So this is about integration by u substitution. So this is just chapter 7.2, Math 211. Okay, so I'm going to just do a whole bunch of them so you can just watch me. They're exactly the same ones I did in class, but just so that you can watch them develop. Okay, so we have this problem. And we see, alright, I see this stuff in here, and I see its derivative is sitting out there. It doesn't, don't worry about the constant, the 3 out front doesn't matter. There's more than one way to deal with the fact that it's not exactly right. I mean, I could just put, you know, a 3 here and then a 1/3 here. And somebody in class wrote a comment that said, how do you know when to put things outside the integral sign? It doesn't matter if it goes outside or inside, it's just that there's not much space. So if I wanted to put the 3 and the 1/3 here, I could. It's just that you usually don't leave yourself enough room for that kind of thing. Okay, but that's not the way I'm going to choose to deal with the problem. In this example, I'm going to do it the standard way, where you just say the thing I want to take the derivative of is just u. And then I just go ahead and take the derivative. But then what I do is I literally just take this piece and I go whoop, put it over there. That's really all I'm doing. And I don't mean to say that trivially, but physically that's what I'm doing, and you are just multiplying both sides by dt. Whatever your small time step is, you multiply by it on both sides. Okay, now the trick is swapping out parts for parts. So I have t squared dt and I have t squared dt, but I can't replace t squared dt with du because there's a 3 in the way. So again, I have to take care of that 3. So my preferred way of taking care of it is to just take care of it right here and say I'm going to make one more step. All right, now I don't have a problem now because this t squared dt is right here and it's right here. I mean, it's all multiplied together, so I can mix the order of these guys around. I can say, okay, somebody said, can I just do this? Can I just move these guys around? And that's totally fine. There's no problem with moving things around because everything is multiplied in this problem. So now we can replace t squared dt like this. Okay, tools. This will be easier to do if I use these kind of eraser options. I'm going to get rid of these guys and, sorry, these guys. And I'm just going to physically swap out 1/3 du because those parts are equal. And I'm going to physically take away this t cubed minus 3, and I'm going to physically replace it with u because it was the same thing. And you see what's left? Everything that's black is still left over. Okay, so that's all I'm doing. Now I go ahead and take the derivative, and it's u to the 11th over 11, but then there's this 3, so I get u to the 11 over 33 plus c, and then I just rewrite that by saying integral. I use the capital I to mean integral when I don't feel like rewriting the whole symbol again. And so it's u, but I'm going to put u back in the t world. That's all we're doing. Okay, so there's that one. Okay, let's do the next one. The next one is really easy. You don't even really need to use u substitution for this one. It's just in this chapter because we can do this. Oops, plus c. Okay, you can say u is equal to e to the minus x, du is equal to minus e to the minus x, and then minus du is equal to e to the minus x. So, oops, and then the dx goes over here. Forgot that guy. Okay, so this whole thing, e to the minus x dx, is just du, right? So this is really kind of silly, well, with a minus. And what does that mean? It means minus 1 times du, and that means minus u plus c, because if you take the derivative and got 1, then you started out with u. So this one is almost easy enough that it's confusing. And the minus of u is up here. Okay, so there we go. So that's how you use u substitution for this problem but I would hope that this problem you would find obvious and you would just pop in the negative sign where it belongs. Okay. Next problem. Okay, you see the parentheses are not necessary, but I'm putting them in to drive a point. So we look at this structure and we say, aha, if I let u equal x squared plus 1, du is equal to 2x dx, I can swap out parts for parts, just like that. And so then I rewrite this. The 2x disappears because it's going away with the dx. So in the old problem you needed a 2x and a dx, but in the new problem you just need a du. That's the whole point of using this technique. And then the e to the stuff is still there, but it's now e to the u. And so the integral is e to the u plus c, and then we just finish this up by saying, e to the x squared plus 1 plus c. So some students, I think you guys got this, but when we were first doing integration, you said, when do we get rid of the integral sign? You should be viewing the integral sign and the d whatever as one unit, kind of like parentheses. And the stuff inside is what you take the antiderivative of. And when you've actually taken the antiderivative, the step of taking the antiderivative is when that symbol disappears. Okay? The same thing when you're using u substitution. Alright, next problem. Elephant prime over elephant. Where have we seen this before? Okay, so we just suspect that we're going to do some kind of natural log thing. And so the denominator is the original function. du is 3x squared plus 1 times dx. So we think, okay, this is pretty straightforward. So this whole piece is here, and it gets replaced with du. Okay, and this denominator is u. I've done the colors this way on purpose to show you everything that was black is the same in both. With the x world and the u world, those parts stay. The fraction bar stays, the integral symbol stays. Okay, and then you just get natural log. You have to use absolute value signs, but then you're done. And that's just equal to the natural log of this junk, whatever it was, your u, and then you're done. Okay, let me get another one. It's another one you did. It works just the same way. There you go. You just generate these pieces, and then you say, I have a t dt in the problem, but I've generated a 4t dt, so I'm going to fix that. Now I'm going to replace all the parts. Again, the t dt disappears together with du over 4. So this piece is being swapped out. The red circles are being swapped out for one red circle. And then the other thing I'm doing is u to the 3 over 11. So this piece is getting swapped out for this piece. And we're allowed to do this. And then we go ahead and take the integral. So it's 3/11 plus 1, which is 14 over 11. And then you'll get 11 over 14 out front. But then that 1/4 stays. Okay? And then, of course, plus c. So you get something obnoxious like, you know what, you can just leave it. I don't care. If you're concerned, just come up during the exam and say, can I just leave it like this? And I'll say, oh yeah, sure. Something this obnoxious, I don't care. That shows me that you know how to do the u substitution. Okay, so what about this silly one I gave? What about, why is that silly? Well, because u is equal to u plus 7. du is equal to du. I'm using different colors just to show you I can actually pull this off. And then this is equal to du over u, which is equal to natural log of u plus c, but That's natural log of u plus 7 plus c, which is way more trouble than it's worth. So for free, you get to add constant. Okay, that part you get for free. So anytime you have some weird thing, you don't really need to use u substitution. If you had cosine of x plus 7, you could just say negative sine x plus 7. The constant comes along for free by u substitution because the derivative of x and the derivative of x plus 7 is the same. You've got that constant of integration, so you just literally don't have to worry about it. Okay, and I think we did one like this. Again, this guy is u. But what do we have? We have an x plus 1, so du over 2 is equal to x plus 1 dx, and then we're going to get du over u, natural log, oops, 2 goes in the bottom, so then we get 1/2 natural log of u plus c, 1/2 natural log, and what was u? It was this mess on the bottom. That was that one. And what else did we have? We had, did we do these yet? I think we did. Again, you just say, aha, it's elephant prime over elephant. Derivative of sine is cosine. And then we have du on top, u on the bottom, is natural log of u plus c, natural log of u plus c. It's really not supposed to be difficult. Some of these are meant to work out very fast, like all these introductory examples. Once you get going, you can just see them and you don't have to really think about them. This guy's going to be u, du is 6x dx, but we don't have a 6, so it's du over 6 is x dx. So this is just 1/6 e to the u du. So you get 1/6. Aha, e to the u is a fun one because you don't have to worry about the, e to the x is its own derivative. So it makes this problem very easy in that respect. And let's see, we had, here we go. We had x sine of x squared dx again. This is the u. Du is 2x dx. Du over 2 is x dx, so we get 1/2. And that 1/2 can go inside or outside, doesn't matter. Sine of u du. The important thing is the SIGN. Notice that this derivative of sine is cosine, so derivative of cosine is negative sine. So when you take the integral, it's the opposite, right? So this is the riskiest part of the whole problem, I think, is getting that correct. And then you end up with minus 1/2 cosine of x squared plus c. And those were all the problems we did in class.